The TKSC is a very simple device. It's made up of just a couple components. First of all, it's about 6 inches tall, 3 inches wide, and 3 inches wide, yep, and 3/4 inches deep, which makes it easier to fit between a seal or a coupling or down in the shaft wherever you can happen to get to the shaft. Makes it a lot easier. The made up a couple parts. It's got a base plate. It's made of nylon, so it does not affect the field, the RF field from the proximity probe. It's made up of an armature that has bronze oil bearings in it to make it slide up and down the shaft very, very easy. The armature holds the proximity probe by using 2 nuts. You can take a 1/4 or 3/8 inch proximity probe or any of the metric sizes up to 0.400 in diameter. Then you have a top plate that holds the dial micrometer, and the top plate can be adjusted. So basically the armature is spring-loaded, and the top plate holds it so you can zero the micrometer out. The test setup is going to be made up of the TKSC, a proximity probe system with the probe mounted in the armature. The proximity probe system is wired to the extension cable, to the proximeter or driver as some call it, and of course you need a power source for this driver. Then the proximeter output or driver output we're going to wire to a digital voltmeter where we're going to measure the negative volts DC coming out of the driver based on gap. So anyway, I'm not going to go through the wiring setup, but we'll go through this. What I do is mount the proximity probe in the armature, make sure that the probe will stick out below the nylon. In other words, it'll actually touch the surface of the shaft. Adjust the top plate to hold it there temporarily. Okay. Then we get it mounted on the shaft by using the webbing that we provide. Now, in a case on your shop, it actually might be a little easier to do this. I'm going to let it dangle just a bit while I connect this. Pull this back up and then tighten the webbing. And there we are. We're mounted. Okay. And you want to make sure this is the same location where the proximity probe is going to be looking at on your machine, the viewing area. Now what I'm going to do is make sure this probe is touching the shaft with the micrometer set at 0. So I set the micrometer to 0. Okay. Then I loosen the top plate, and I'm going to push down until the proximity probe touches the shaft. All right. Okay, we have the proximity system installed. We have it powered up. We're showing minus 1.34 volts on the digital voltmeter. Our micrometer is set to 0, and our proximity probe is against the shaft, or in other words, 0 gap. Okay, what we're going to do now is we have a choice of running a complete probe calibration graph. We have an Excel sheet available on the STI website under 80 probes that automates the system. You enter the numbers every 5 mils, or the voltages every 5 mils, and it'll automatically graph it for you. You need to enter things like the proximeter and serial number and model number, cable, and eddy probe itself. Customers like this because it ensures that they know what they have. You also can take a very quick approach to this too. We currently have the probe touching the shaft set to 0 mils. We know that most proximity probes are gapped between 50 and 60 mils. So I'm going to roll this out to 50 mils. That's 25, 30, 40. That's 50 mils right there when I come around on the 0 twice. And I have minus 9.35 volts. Now I'm going to roll around 10 more mils. 5, 10, and I've got 11.42 volts. So that's 2.07 volts DC difference, right? We moved the micrometer 10 mils. So we divide the 2.07 by 10 mils, and we get 0.207 millivolts a mil. 200 millivolts per mil is standard for API 670 from looking at 4000 series steel. anything from 190 to 210 millivolts would be considered in calibration. So you can tell right now that we're in good shape on this one. If this had been an exotic metal or something we didn't know, or chrome surfaced or something like that, we might have a number as low as 167 or even high 237. So it's important to know what your calibration is for an unknown piece of metal. If you know what the metal is, you're in much better shape. Okay, back to doing a standard calibration curve. What we do is we go back to the 0 point, which is when the shaft is, or the proximity probe is touching the metal. Now we start moving out in 5 mil increments. So at 5 mils, we write down the voltage, 1.352. That's a negative, by the way. We go to 10 mils, so we're going to go every 5 mil increments. And you'll notice that it's fairly easy to line up. We got minus 1.529. At 15, we got minus 2.336. You see the probe is actually coming in range now. And at 20 mils, we got minus 3.321. And we keep doing this for 5 mil increments until we roll off the other end, and you'll actually see when the probe quits responding. Okay, what we've done is we've entered all the handwritten voltages we wrote down as we adjusted the dial micrometer. We've entered them on the Excel worksheet that's available to you on the stiweb.com under Eddy probes. And we simply typed in these numbers, which you could have done at the same time as you were taking the values. And the graph will automatically do a curve for you along with the deviation from what's acceptable for API 670, which is 5%. For what we're trying to do with the shaft calibrator is determine what our calibration is. Most probes are gapped somewhere between 45 and 65 mils, usually in the 55 or 50 mil category. And what you see here is at 65 we have 12.82, so we're going to use a calculator. And we're going to enter 12.82, and we're going to subtract 8.66, which leaves us 4.16 volts for 20 mils. So we're going to divide that by 20 mils, and that gives us 208 millivolts per mil. Standard calibration for API 670 is 200 millivolts per mil. 5% is allowed, so that's 10 millivolts. So this is within spec. It would have to be over 210 or below 190 millivolts for it to be out of spec. So essentially we're looking at 4000 series steels, and we're dealing with a system that's in spec, and our calibration is 208 millivolts per mil.